hopefully somebody got a chance to look at these videos and see if it's better having it direct on versus the side. Some people were complaining about the glare from the window when it was on the side because of the reflections. But anyway, Google Classroom. All right, so next unit is about bonding. And there are a number of types of bonds. We're going to talk about 5 or 6. The first two we're going to talk about are the most basic types of bonds, when the electrons are given or taken, or electrons are shared, like in the video, which I think is awesome. And if you want to watch the video again, YouTube. You just YouTube search for atoms and their electrons. But an ionic bond forms when, just like chlorine steals sodium's electron, if one atom takes an electron from another atom, we call that an ionic bond, because they become ions and then they stick. A negative ion will be attracted to a positive ion. That's an ionic attraction. So when electrons are given or taken, that's an ionic bond. It happens a whole bunch very often, and then you get a bond. Now this only happens with metals and nonmetals. So you only get an ionic bond when you have a metal from the left side of the periodic table bonding with, when I say left, I mean left. These are all metals. Metal, 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 metal. You have a metal from the left side of the periodic table bonding with a nonmetal from the right side of the periodic table, then you're going to get an ionic bond. And you're going to get an ionic bond because the electronegativity differences are huge. You get fluorine's like, I am the most electronegative. And you get sodium's like, I am the least electronegative. Give me your electron. Okay. Now I have a negative charge. And I have a positive charge. Mix it together. I prefer my instructions in the form of a puppet show. So that's an ionic bond. When a nonmetal takes an electron from a metal, then you get an ionic bond. One becomes positive, one becomes negative, and they stick. Sodium chloride works like this. A lot of the solid compounds that we play with in labs will be ionically bonded so they can dissolve in water. Now, covalent bonds are a little bit different. With a covalent bond, the contract works something like this. Atom 1 says, I need 2 electrons. Atom 2 says, I need 2 electrons. Hey, Atom 1, tell you what, if you give me 2 electrons, I'll give you 2 electrons. That sounds good, Atom 2. This way, I'll have an octet sometimes, and you'll have an octet sometimes. But since the electrons are moving so fast between us, it'll look like we both have an octet. That's how covalent bonds work. One atom gives an electron to the other atom. The other atom gives an electron back. They share. So it looks like part of the time, one atom has a completed octet, and part of the time, the other atom has a completed octet. But because the electron moves so quickly between them, it appears to the outside world that they both have an octet. Does that idea make sense? So they share. It's kind of like, I want to get the new Call of Duty game. I have $30, and you have $30. Let's pool our money together and buy it. Half the time, it'll be at your house, and half the time, it'll be at my house. The analogy breaks down when that time speeds up so much that your parents can't tell who has it. It seems like you both own it. You gotta get the deluxe edition?
You gotta get the Modern Warfare Remastered. The new one's crap. You gotta get the remastered.
I'll keep that in mind.
Because, I mean, $80.
I know, as expensive as video games are, they were a lot more expensive when I was your age. Legend of Zelda was $60 when I was in your age, in the 80s. $60 now is worth about $85 or $90. So yeah. Anyway, so that's ionic and covalent. Any questions? I play PC games. All my games are cheap. I just wait a couple weeks for a sale. Okay, now, review. Quick review about ions. You don't need to write this down because you've already written this down. Well, most of you. So again, remember, an ion is an atom that has gained or lost an electron. An ion is an atom that has gained or lost an electron, which means it will have more electrons than protons, or less electrons than protons. If you gain an electron, what does your charge become? Negative. And what do we call that? becomes a bigger negative ion, which we call a negative ion, anion. On the other hand, sodium gets rid of an electron. It gets rid of an electron, minus an electron. It becomes a positive ion, which we call a cation ion. Positive ion. Okay, so what do these ions do? Well, if you get enough of them together, they stick. And remember the octet rule? Pretty important. If you're an atom, what is your ultimate goal? In atomhood, what is your ultimate goal if you're an atom? Get an octet. That is your ultimate goal. If you've got 7 valence electrons, you spend all of your time trying to get one more. If you've got 1 valence electron and an octet in the next shell, that 1 valence electron is really not that important. You don't want to get rid of it, but you're not going to hold it very strongly. Okay? So your ultimate goal is to get an octet. If you've got 2 valence electrons, you're going to try really hard to get 2 more. Sorry, if you've got 2 valence electrons, you're going to try to get rid of those 2, so you have your next inside shell as an octet. If you've got 6 valence electrons, then you're going to try to get 2 more, so you have 8. Give me a thumbs up if all this review is a review and you're ready to move on. Okay, no questions? All right, moving on. Okay, so you got chlorine and you got sodium, and what do? What do chlorine and sodium do? The ions. They attract. Like in the video, chlorine stole the electron from sodium, and then chlorine got really big and negative, and sodium got really small and positive, and they stuck. Boop. Because they're electrostatically attracted to each other. Okay. Well, it turns out, if you got a whole bunch of them, a whole bunch of chlorines and a whole bunch of sodiums will form what's called a crystal lattice. So you take that chlorine and sodium again, and you combine it with 1 billion more chlorines and 1 billion more sodiums, and all the ions are attracted to each other, and they form a 3-dimensional grid called a crystal lattice. We can't see ions with our eyes. We can't even see ions with a microscope. But you can see the shape of the crystal lattice with your eyes. Anyone ever notice what shape a table salt crystal is? Well, next time you're at the restaurant and your grandparents are putting salt on their food, pour some in your hand and look really close at it. You'll notice it will be a cube. It will be a cube because the crystal lattice for sodium chloride is cubic. It forms a cube. So all the crystals will come out cubes. Pretty cool. In fact, even if you take some salt and grind it into a powder and put that powder under a microscope, that powder will be tiny little cubes. Even if you put it into an electron microscope, tiny cubes. They stay cubes because the crystal lattice for sodium chloride is cubic. It forms cubes. Quartz forms hexagons. If you look at quartz under an electron microscope, it forms hexagons. Big hexagonal crystals. That's the way the atoms are arranged. I have a video clip, which is excellent. So I'll show it to you.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution.
Okay, let's take a look at these water molecules. Water molecules are usually drawn one particular way, for reasons that might not make sense to you yet, but will very soon. They're almost always drawn Mickey Mouse head. They're almost always drawn this way. Why? It turns out, question, Moran, guess?
Why is it drawn like that?
Yeah.
It's easy to see the hydrogen bonds.
Makes sense. Anything else you'd like to add? It turns out, later on we're going to learn something called Lewis structures, and it turns out oxygen has 2 electrons hanging out over here. These are called paired electrons. And because of it, if you were to draw the electron density around water, it looks a lot like that. This is the electron density over here. It's got lots of electron density down here. So what charge are electrons? Negative. So this end of the molecule is negative-ish. So we draw a little script S. It's a Greek letter delta. We draw a little script S with a line on it. That represents a partial charge, negativeness. It's not -1, -2, -3. It's negative-ish. Now, this end of the molecule is negative-ish. What's that end of the molecule? Positive-ish. This end of the molecule is positive-ish. And if you have a molecule that has a positive end and a negative end, what do we call it? Polar. Exactly. We call this polar. This is a polar molecule. And this concept is probably 1/3 to 1/2 of everything in this unit. The idea that some molecules are polar and can dissolve ions. Take a look.
The ions on the surface. Substance such as sodium chloride is placed in water. Water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Okay, this is huge, guys. This is big. Look at the side of the water molecule that is attracted to the anion. What side is attracted to the anion? The hydrogen side, or the partial positive side. So the partial positive side of the water molecule is attracted to the anion and pulls the anion out of the crystal. On the other hand, the partial positive side of the water molecule attacks the what? The partial negative side attaches to the, so water molecule's partial negative attacks the what? The positive ion. So that oxygen side is the partial negative. That oxygen side attacks the cation and pulls the cation out of the lattice. So this is how water dissolves things. We tend to call water the universal solvent because it's really good at dissolving things because it is very, very polar. Anyone ever tried to dissolve wax in water? It doesn't work. You can't dissolve wax in water. Does wax have ions? Nope. Because if it did, water could attack it. So water is what we call a polar solvent. Polar solvents are really good at attacking polar things or ionic things. Does that make sense? Nod your head if this concept makes sense. No questions? Not getting a lot of participation. Some people are just bored. I'm sorry. I'm sorry you're so bored. Am I going too slow? Okay. Understand. I'll go back. Okay. So, what's an electrolyte? What's an electrolyte? Yep. And Brondo. Yes. Electrolytes is Gatorade. You know where else you find electrolytes? Yeah, the water you're drinking has electrolytes. Bottled water has electrolytes because they put things in it to make it taste different. Electrolytes are solutions of ions that conduct electricity. There's two important parts about that statement. An electrolyte is a solution of ions, and because it has ions, it conducts electricity. And there's a whole unit we're going to work on next spring about solutions, and ions is a huge part of that. But right now, just realize electrolytes are solutions that conduct electricity because they have ions. They conduct electricity because they have ions. Rondo has what plants crave. Okay. Shall we move on? Let's move on. Okay. Formula unit. Realize that ions come together to form crystals in real life. I mean, some things that we can see. So negative ions and positive ions come together and they form crystals. And when you get billions of positives and billions of negatives together, they form huge crystals called lattices. But the most fundamental building block is called the formula unit. The table salt that you shake on your food, or that is all over your French fries, has billions of positive ions and billions of negative ions, but its formula unit is still just NaCl. So even though your table salt, spill it over your shoulder, put it on your French fries, has billions of ions, the formula unit, the most basic structure, is still just one Na and one Cl. The empirical formula, this is where my model breaks down a little bit because it's really simple. The empirical formula is the number of each ion in that crystal. In this case, simply one Na and one Cl. Empirical means with numbers. It's probably a word you should add to your vocabulary. Empirical means with numbers. Unfortunately, with this particular example, since sodium chloride is just one Na and one ACl, or one Na and one Cl, the empirical formula and the formula unit are the same thing. The formula unit is just NaCl. The empirical formula is one Na and one Cl. That's not always the case. Sometimes the empirical formula will be different than the formula unit. If the formula unit has multiple ions, maybe it's 3 of one and 2 of the other, maybe it's 4 of one and 2 of the other. But in general, empirical formula is just the number of those ions. And once again, you put them together, you get the crystal lattice. Okay. Any questions about this before we move on to metallic bonding? Okay. Metallic bonding. Pretty cool. Metallic bonding occurs due to the electron C model, something called delocalized electrons. And I'll show you what that looks like in a second. Delocalized. Okay, we remember that we're going to play with 3 types of orbitals, S, P, and D. What is the shape of the S orbital? the ball, the sphere. So an s orbital is just simply a sphere. What's the shape of the p orbitals? Dumbbell. The p orbitals look like that. There's the x and the y and the z. Here's the crazy thing about d orbitals. If you remember from the last unit, d orbitals are really long and narrow. And because they're long, narrow dumbbells, in the presence of other d orbitals, they overlap. So you might have a nucleus there with a d orbital electron that overlaps with this d orbital electron. You might have one down here, and this d orbital electron, or orbital electrons, might overlap with that orbital electron. So because the d orbitals are so long, they can overlap into other atoms' orbitals, which makes them do something kind of interesting. The electron in this orbital is just cruising along, gets lost, and all of a sudden it's in this orbital. Gets lost again, and all of a sudden it's in this orbital. So the electrons can cruise between orbitals. That's what delocalized means. It means the atoms of the d orbitals, the d block electron, the atoms of the d block have electrons that are delocalized. They're shared amongst all the atoms. If you ask, hey, iron, where are your electrons? They'll be like, I don't know, they're all over the place. They could be down the road with some other wire or some other atom. And hey, cobalt, where's your electrons? I don't know, they're shared with all the other atoms. So that's how the d orbitals work. Because the orbitals are so long, they overlap. Now this only happens in the d block and aluminum. So elements in the d block and aluminum can do this. Why aluminum? It's way beyond the scope of this course. I don't entirely understand it myself. It's how the electrons can actually move into orbitals they shouldn't be allowed into. So aluminum can actually push its orbitals into something that looks like a D. It's called hybridization, and it's not something we're going to get into this year. Okay. So the important thing is they're delocalized. Now this is great because that means you can take a metal and you can bend it and change the location of the protons, and the electrons will still flow between them, giving them some pretty cool properties. Not the least of which is they're malleable and ductile. They're good conductors of heat and good conductors of electricity. Remember, properties of D block metals, they're lustrous, meaning they're shiny. We're like, metals are shiny. Metals are luster. They're malleable. They're malleable because you can hammer the metals together and you can move the nuclei around, and the nuclei will still be able to overlap the electrons in the d orbitals. You can do crazy stuff with them. Like you can hammer them to something just like a few atoms thick. They're ductile, meaning they can be drawn to a long wire, and they conduct electricity really well. Because these orbitals overlap, you can drop in an electron on one end, and an electron will pop out on the other end. That's what happens in your cell phone right now. What happens in the lights, the fan. One electron goes into one end of the wire, electron pops out the other end of the wire. It also means they conduct heat very well. When we talk about conducting heat, what we really mean is the atoms are able to vibrate very, very well. If atoms can vibrate well, they conduct heat well. If they can't vibrate well, they won't conduct heat well. Because we're going to learn later on that when we talk about heat, what we really mean is molecular movement. When you put something in your microwave, what you're really doing is causing the microwave or to cause the atoms to move more. That heats it up. Okay. Give me a thumbs up if you're with me so far. You understand this crazy concept. Okay, questions? Let's move on. Okay, so covalent bonding is the bulk of this unit is about covalent bonding and what happens with covalent bonding. Covalent bonding happens when electrons share electron pairs. And it only happens with nonmetal atoms. Electrons share pairs of electrons. Or atoms, sorry, atoms share pairs of electrons. Now, covalent bonding only happens between nonmetal atoms. If a metal and a metal get together, you get metallic bonding. If a nonmetal and a metal get together, you have ionic bonding. And if a nonmetal and a nonmetal get together, you have covalent bonding. Sometimes covalent bonding is called molecular bonding. It's kind of an old term that we shouldn't use, but sometimes we still do. We have a lot of old people out there. But we should call it covalent bonding. Now, where do you find the nonmetals? Yeah, this side of the P block. So you got metals over here, you got nonmetals down the middle, and you got you have metalloids down the middle, and nonmetal carbon, phosphorus, selenium, iodine. So you're a nonmetal layer. Not very many nonmetals, but the vast majority of the atoms that we deal with are metals, but not very many nonmetals. So when nonmetals want to bond with each other, they share electrons. Atom 1 says, give me an electron, I'll give you one too. Atom 2 says, sounds good, I'll give you one, you give me one, and they share. That sharing produces an electron pair. Electrons are always shared in pairs, one from each atom. The diatomic molecules, of course, are all nonmetals and all bond covalently. Bromine says, I need one more electron. Hey, other bromine, give me one. Okay, we'll share. That's what they do. Bromine shares with bromine. Same with iodine, and chlorine, and hydrogen, and fluorine. Oxygen's special, though. Oxygen needs how many electrons to complete its octet? Take a look. 2. Yeah, oxygen needs 2. So oxygen says to another oxygen, hey, oxygen, you need 2 electrons to complete your octet. I also need 2 electrons to complete my octet. Another oxygen says, that's a good point. You need 2, I need 2. Tell you what, let's share 2. I'll give you 2, you give me 2. That's a good deal, oxygen. I'll give you 2, you share 2 too. So that forms what kind of bond? A double bond. That forms a double bond because 2 pairs of electrons are being shared. Now nitrogen is even stronger. Nitrogen says, dude, I need 3. Hey, other nitrogen, would you like to give me 3? Other nitrogen's like, that sounds a good deal. I'll give you 3, you give me 3. Sounds good, let's do it. So they exchange 3 pairs of electrons, forming what kind of bond? Triple bond. Forming a triple bond. Okay, so doubles and triples. Double bonds are stronger bonds. Triples are the strongest. Triple bonds are the strongest bonds. Double bonds are stronger than single bonds. old-timey explosives use nitrogen compounds because when nitrogen bonds or has its bonds broken, releases a lot of energy. There's a lot of energy in those triple bonds. Single bonds don't have as much energy. There are a lot of them, but they don't have a lot of energy. Now, what about length? This rubber band is probably going to break, so I'm not going to extend it really a lot. But if this represents a single bond, I double it, this would represent a double bond. Right? A double bond is what in length compared to a single bond? Shorter. And if I double it again, I got a triple bond. And a triple bond is even shorter. So a single bond is the longest bond, and a triple bond is the shortest bond. Now, energy. This is where we're going to end today. Energy. This is one of those really slick concepts. Atoms will bond at a distance to reduce their potential energy. They want to be at the lowest energy state possible. So bonds want to be in the lowest energy state possible. Now, this takes some imagination. Are you ready for imagination? Okay, let you wait. I'll wait till you're done scribbling. Never heard of this person. Okay. Oh, Camilla. Camilla. Okay. I said Carmella. Okay, I said Carmella. Camilla. Carmella. I have a friend named Carmella. Okay, so what causes one atom to bond with another atom? Think about this. What causes one atom to get close enough to attract, what causes one atom to get close enough to bond with another atom? Attraction of what for what? The attraction of the protons of one atom for the electrons of another atom. There's an attraction. Now here's the thing. The protons, you guys still have a minute. The protons, or you don't. Okay?